Hello, welcome back to part B of Abaqus tutorial 10, and this tutorial is on the analysis of a lug-pin assembly. The problem statement will not be repeated here as it is already covered in part A. So this is a problem statement. You can refer to part A for the same. So this part of this tutorial, that's a part B, will cover modules, namely interaction, load, mesh, job, and interpretation of results through the visualization module. So let us go to Abaqus. So let us just start with interaction module. So the interaction module will tell Abaqus what are the surfaces that are in contact and what would be the contact surface properties. So let us first proceed to define the interaction property. So we'll just press this. So interaction property, I will call it as say lug-pin. Here select the type as contact, continue. And here we need to define both the normal as well as the tangential behavior. So in the mechanical, select the tangential behavior, and let us don't use a frictionless. Instead, we shall use a penalty function, and let us provide a friction coefficient of 0.30 between the surfaces in contact. Next, let us go for the normal behavior. In the normal behavior, we'll choose the pressure over closure as the hard contact, and we'll keep other options as the default. Okay, so we have defined first of all the interaction property. Now let us define the interaction, create the interaction. Now in fact Abaqus has various methods. The most commonly used are the general contact as well as the surface to surface pair. So let us proceed for creating the interaction. So we shall use create the interaction, and here as you can see that let me say that this is interaction. For example the lug-pin, and here as you can see, if we are going to the initial step, you can see that there is one method available as the general contact, okay, which is the easiest method of specifying the contact interactions, and there is also surface to surface contact standard. Okay, so here so let us proceed for one option that is available here, that is find contact pairs. So selecting the surfaces manually, this will take a lot of time in Abaqus. For simple models it is okay. For example, even for this simple tutorial, we have got almost 9 surfaces in contact. That's lug to lug as well as the lug to pin contacts. So we can use the facility available in Abaqus, that is find contact pairs. So if you press this, it will ask you. So I want to find out all the contact surfaces that are within a distance of 1 mm. So all other so you can find contact pairs. So look here. So here we can see that Abaqus automatically spotted. Okay, 7 surfaces, 1, 2, 3, 4, 5, 6, 7. So if you would like to see which are these surfaces, for example here CP1 lug 2. Okay, so just highlight it. You can see that yes, this provides us the contact between the lug 1 and lug 2. That's a common contact. You can see that circled over here. And for example, suppose you are interested in seeing another one, pin 1 and lug 3. So this provides us the shank to lug 3 contact. So means that we have got altogether 7 pairs of surface contacts, and here you can see that there are many parameters available here. For example, the type. So the type you can just slide it and see what it is. Interaction. And in Abaqus, there are 2 types of sliding. For example, the finite sliding and small sliding. This requires a lot of explanation. So here I have selected as a finite sliding. So discretization is surface to surface. And as you can see that the property we have already defined, it is already taken here. That's a inter property lug-pin. And adjustment of the geometry is also one main parameter, because you can have a strain-free adjustment. You can have what we call as the interference, the fit adjustment, etc. All those things, and the surface smoothing. These are the various parameters. These are all kept default here. So you can just select OK. So this means that here we have automatically specified the surfaces where the interaction property will be applied using the find contact pairs, and this makes made our job of specifying the interactions very simpler. You find, so that's all about the interaction. Now you can go back to the load. In the load module we need to apply both the boundary conditions as well as the pressure loading. So let us start applying the boundary condition. Okay, so I'll say that bc pint, okay, fine. And so for example we can call it as a, for example, bc fixed. Okay, we are fixing the two ends. Okay, so this should be applied in the initial, and it is the displacement rotations. Continue, and Abaqus asks you to select the surfaces. So you can just rotate it a little bit. Okay, and yes, these are the two surfaces where we would like to apply the boundary conditions. So just select these surfaces using the shift key. Okay, select it. Fine, good. So done. So you can just select, for example, U1, U2, U3, or if you want to completely fix it, you can select UR1, R2, R3, etc. also. Okay, fine. See, yes, you can see that the boundary condition is applied. Okay, now we need to apply the so-called pressure loading on this face. So we can go back to this create load. So we can see that this is the load on the lug, load on the lug, and obviously this has to be selected in the analysis step that we have already created. It's a pressure loading, so select the pressure loading properly. Okay, so continue. So now we need to select the surfaces. Select these two surfaces using the, it is already selected, done, fine. And now apply the pressure loading, and the pressure loading I would apply 75 MPa, and apply it gradually using a run function. Okay, so okay, fine, we have to change it a little bit because it has to be in the other direction. So you can go back over here, you can just edit it, and instead of 75 you can just put a minus 75, and that should solve our problem. Okay, so yes, it's applied properly. So this means we have completed the boundary conditions as well as the loads. We can go back to the meshing now. So in the meshing, obviously when we have uploaded the various parts in the assembly module, we have very specifically stated that the instances are such that they will be meshed in the part. So select this in the part. Okay, so let us first proceed for meshing the leg, because we are going to do the meshing by parts. So we have to mesh first the leg, then the pin, right? So let me just take away like this. So first what we do is, we know that as far as this kind of a geometry is concerned, this circular area represents a sort of a stress concentration. So means that we have to use a finer mesh over here. So let us use a global seed of, for example, for this, considering the size of this member, let's apply a global seed of 4 mm in size. So you can see that is already applied. And we want to refine this is circular area a little bit more, right? So let us apply a local seeding also. So go to the local seeding, and to the local seeding it asks you select the regions where you want to do the local seeding. I want to uh, select both these edges. So select these two circular edges where I want to apply the local seeding. Okay, so that's okay, and so done. Now in the local seeding, I want to do it by the size, no bias. So let me use the a local seeding which is smaller than the global seed of 4 mm. So here I'm using a local seed of 2 mm. Apply. Okay. So you can see that this edge is okay, having much more smaller edge elements. So now we can proceed for the mesh control. So proceed for the mesh control, and first select the regions. So here we shall use the hex element shapes, and the technique where we have the hole, the best technique will be go for the sweep and the middle axis and tick this, minimize the mesh transition. This is okay, fine. Now we can go for the element selection, assign the element type, select this once again, done, and go for the standard 3D stress element, linear, geometric order linear will be good enough for this problem. And read these elements. It's the element that we have used for the lug is C3D8R, which indicates an 8-normative linear brick element with a reduced integration. So this okay. So this means we are now ready to mesh. Press this button. So yes, so you can see that yes, this part is properly meshed. So you can see that yes, we have used a smaller sizes very near to the circular horn because we expect a larger stress concentration in this zone. Now, Abaqus also provides us a verification tool here to see that whether the mesh, okay, that is developed is healthy for the analysis or not. So you can just select this. Uh, okay, so verify it. Select this one, and you can specify what must be the limits of the angles, what must be the aspect ratio. For example, here I ask the Abaqus highlight all elements with an aspect ratio higher than 3. So highlight it. So here we see that yes, we have got almost 1.03 elements with more than 3 aspect ratio, and it says highlight over here. And the worst aspect ratio is 1.72 and average is 1.24 is acceptable, and there are no errors or the warning messages. So it does mean that the mesh is good enough for my computations. Okay, so now we shall proceed for the second part, that is our pin assembly. In the pin, obviously what we do is that we'll go for only one kind of a sizing, that's a global sizing. So I will go for here, I will use it as a 3 global sizing. That must be good enough for my, I think is okay. And go for now the mesh control procedures, select the member, okay, this. And here what we do is that we'll use the tet element, and we'll use the technique for the meshing as a free. That must be good enough for us, okay. And now let us proceed for the element selection. Okay, now select this element. Okay, fine, done. And here we are using the standard 3D stress element, and let us go for the linear one. And so the element that we are using is okay, so if you are going for the quadratic, you can go for the quadratic, whereas C3D ton element, as a ton order quadratic tetrahedron will be used. You can select it, okay, and we can proceed for the meshing. And yet just press mesh. Yes, you can see that yes, it's a nice meshing, there is no issue at all. So we need not to verify it. So this means that the meshing is complete, and now we are ready for submitting our job. So just so we have to create the job first. So let me see that is a job, and let me see that's a lug, and just continue. Okay, this is okay for me, and then just submit it. Okay, so you can see that yes, the job is submitted and it is under running. Okay, fine. Okay, fine, our analysis is complete and we are in the visualization module to review the results. And in the results, we'll very specifically see the von Mises contact stresses as well as the displacements. And for this problem, let us see the von Mises distribution in the middle lug, which is critical for us. So we'll select the middle one first. So I would like to remove for the time being from my display the pin that is removed, and let me also remove lug 1, remove, okay, fine, and lug 3 also I will remove, okay, fine. So here you can see that yes, this is how the stress distribution looks like in the middle lug, which is very critical for us. And we find that yes, as far as the middle lug is concerned, the stresses have gone up to the level of say 239.6, okay, 239.6 Newton per ohm square, which obviously indicates that yes, the material has yielded because the lug is made up of aluminum with a yield stress of 125. So let's see how the stresses have finally reached to these values. So we can use this. So this shows the how the stress has gradually developed. You can see that yes, it is developing over this area and spreading to the other areas. Okay, fine. And we find that the maximum von Mises stress is of 239.6. It is going to be very near to its ultimate stress level, right? It does mean that this material must have undergone a lot of a strain level which is very near to the ultimate strain. So suppose you would like to know the portion of this lug where the materials are already yielded. The best way to do that is you can go to this control options. Under the control options, there is a facility to specify the limits. So here, rather than auto compute, specify it as show me all regions where the stresses are higher than 125 MPa. 125 MPa is the yield stress for aluminium. Apply. Okay. Now look here. You can see that yes, 125 more than 125 is this gray area. This gray area. So you can see that how this is the when the stresses exceed that. You can say that for example yes, yes, yes. You can see that approximately at this step. Okay, the stresses started yielding. Okay, you find that yes, this look into the gray area. This indicates where the stresses, the one measure stresses are exceeding your the yield stresses. Aluminium, yes, and you will find that yes, this circular hall, it is now turned to an elliptical one because of the high strain levels that is getting accumulated in this part. So that is all regarding the stresses in the leg part. Now let us also see the stress in the bolt. So what we can do is go here and remove this. Let us include this pin. Okay, add this pin into this and let us remove this lug 2 now. Remove. Okay, so we are going to inspect only the stresses in the bolt, and we find that the maximum stress here is 539.6 and the yield stress for the bolt is on the order of 640. So we don't have any kind of a problem as far as the bolt is concerned. And here for example you can just remove the criteria that we set. Let the limits be set by auto compute. Apply. Okay, so this is how the stress distribution takes place over here, right? So we find that the maximum stress is on the body of the shank is on the order of 539. So we don't have an issue as far as the bolt is concerned. Now we would also like to see the distribution of the contact stress. So let us go back to this and we'll just include lug 2. That's a medium one, middle lug. So just add it and let me take back this my. Okay, fine. So you can see that here the contact stresses. Okay, so go back to CPRF. This is contact pressure. You can see that the contact pressure maximum is for 46.9 Newton per meter square. And obviously, as expected, okay, we find that the contact stress is getting rather mobilized on this edge because when this plate is cooled, we expect that the bolt will be in contact with this side of the surface. So you can also see how the contact stresses have developed all throughout the analysis. Okay, so you can see that initially it is a small portion. Yes, it is gradually increasing, okay, and it is spreading to more areas, right? So this is all regarding the contact stress distribution. You would also like to see how the displacement behavior, the displacement response of this entire assembly. So let us flip this entire one. So and then here again we would like to see, for example, the deformation behavior of this middle lug. So you can just again select only the middle lug. Middle lug, let us keep lug 2 there. Lug 1 remove and lug 3 also we can remove and let us keep the bolt also there. So that's good enough for us. And let's go for inspecting the deformation behavior. You would like to see the deformation in the x-axis. So means we'll be selecting the U1. So here you will find that we have maximum of say 5.076 okay mm. And now if you would like to see the deflection a little bit a larger scale, you can also go to the common, that is a common plot option. Here for example you can see instead of 5 you can provide it as 8. Apply. Okay, now let us see how the displacement has so just zoom it a little bit. Okay, fine. So you can see that how the middle lug has moved with respect to the bolt. Yes, you can see that yes, it is moving out. So you can see that the tearing of the lug takes place across the bolt interface. That's why you find that if we take it a little bit to this side, you find that now the hull is almost, look here, this is an oversized hull. Okay, because of the lug being pulled, okay, to the right, you find that it is shape has now turned to the oval. Okay, so this is all regarding the deformation behavior of the leg, and we come to the conclusion that yes, the leg assembly, okay, the leg has yielded and the bolt is strong enough. There is no problem as far as the bolt is concerned, and the deformation response and the contact and the von Mises stress distribution reveals that yes, Abaqus has properly modeled the contacts and the interactions between these surfaces. So that's all. So we'll come out with a very interesting tutorials next week. Thanks a lot for listening.